this fundamental property of floating point representation. So there are two properties that we will be talking about. One is floating point representation itself. That means when you enter a real number, how does it get rounded off? What is the floating point that represents that number? So that is according. So this is nothing but we are just rewriting the definition that we wrote earlier for machine epsilon. Okay. So what this is saying is that if you take any real number x, then there will be some epsilon with mod epsilon less than the machine epsilon, such that the floating point FLX means floating point representation of x. Okay, so the floating point representation of x is x times 1 plus epsilon. So what this means, well, x times 1 plus epsilon, you can write as x plus x epsilon. Okay, so we can rearrange these terms to write FLX minus x over x, right? So I can bring x to this side. So FLX minus x over x equals epsilon, correct? I take the modulus on both sides. So I get mod of FLX minus x over x is equal to mod of epsilon, and this by assumption is going to be less than machine epsilon. So what does this mean? Means that if you are given any real number x, you can find floating point representation of that x such that the relative error, okay, is less than, is bounded above by machine epsilon. Essentially, that's what we are saying. The relative error of this representation, when you represent x by FLX, this relative error is bounded above by the machine epsilon. So for any real number, you will be able to find a floating point representation that satisfies this property. Okay, so the worst it can get is as high as machine epsilon. The error cannot go above machine epsilon. So this is about just representing a real number. Okay, and then but you are also performing some operations with the represented numbers, correct? So one also has to talk about floating point arithmetic. Okay, so this is only floating point representation. Let's talk about floating point arithmetic. Okay, so suppose you have some arithmetic operation x star y. Okay, and suppose the x circle star y here denotes the result, that is the computed answer. Okay, so you're taking the actual real number x, the actual real number y, okay, and applying whatever operation, say addition, subtraction, multiplication, division, and looking at the answer that comes up. Okay, and that answer is denoted by x circle star y. So you have the arithmetic operation on the one hand, which is the exact answer that is expected, and x circle star y denotes the computed answer. Okay, so how are these two related? So that is this fundamental property of floating point arithmetic, which says that if your machine follows IEEE standard, okay, then for any xy, if you take any real numbers x and y, then x circle star y will be x star y times 1 plus epsilon. Okay, again rearranging this as before, we see what this means is that the relative error after or the relative error in the computation. Okay, so this is the computed number. This is the supposed to be the actual arithmetic operation, and what we have on the left hand side here is the the relative error in the calculation. Okay, so relative error is going to be bounded above by machine epsilon. So for any computing machine that satisfies the IEEE standard, it is assumed that these two properties are satisfied, which means the representation error for any real number is not higher than machine epsilon, and for any computation, the rounding of error is also relative error, okay, is also not above machine epsilon. Okay, so these are two properties that we will assume throughout, and when we do stability analysis, we will always say that on a machine that satisfies IEEE standard, then which means on a machine that satisfies these two fundamental properties of floating point representation and floating point arithmetic, the following holds true. Okay, so that is how we will have our stability analysis. Okay, so everything will be based on these two properties. Okay, okay, so So first, because we will require this notation as we go forward, we have to talk about what is the meaning of this notation. This is order to the order of machine epsilon. Okay, so or something is to the order of machine epsilon. This notation, in general, the notation means that if phi of t is to the order of psi of t, this means there is some constant c such that for all t, either t going to 0 or t going to infinity, okay, as the case may be. So for all such t, or in the limiting behavior of t, mod of phi t is bounded above by some constant times mod of psi t. Okay, so if that happens, then we say that phi of t is to the order of psi of t. Here it is important to note that the c should be a should does not change according to t. Okay, it's a uniform constant which will work for all values of t. Okay. So just like when we were doing conditioning of a problem, we defined a problem to be a function from the set of the vector space of data to vector space of solution. Similarly, we will view an algorithm also as a function. Now we'll call it f tilde. Okay, so for an underlying problem f from x to y, the corresponding algorithm will be f tilde. Okay, f tilde from x to y, where x and y, like before, are non-vector spaces of data and solutions. Okay. Now there are uh, notions of how good an algorithm is. Okay, so we have to. So first of all, the best thing will be if the algorithm is accurate. Okay, so what is the meaning of accurate? First, you will never get the actual. If you're doing hand computations and the answer, whatever answer you're getting, you will never get it by a computer calculation. Okay, and that is because of rounding point error. So that's a given. Okay, that your hand calculation will never equal the computer calculation up to the last decimal. Okay, whatever last representation is there. Okay, so that is a given. So now you have to start thinking about, okay, so if we cannot get the exact answer, what is the error? How much is the error? Okay, and so talking about how much the error is or how much error is acceptable gives us all these notions of how good an algorithm is. So first notion is accuracy. Okay, so we will say that the algorithm is accurate if this relative error, okay, is to the order of machine epsilon. So what is this relative error? This f of x is the actual answer. Okay, f is the actual underlying mathematical problem, x is the data point, and so f of x is the actual answer. You can think like this is hand computation maybe. Okay, minus f tilde x, this is the computed answer. Okay, computed answer at the same data point x. So what you have on the left hand side here is the relative error in computation when you are using the algorithm f tilde. This relative error in computation, if it is to the order of machine epsilon, then we will say the algorithm is accurate. But it turns out that in many cases, accuracy is a very high ask. Okay, it is very difficult to achieve accuracy. Okay, and there are, because of these rounding errors in the various steps that accumulate, it is very rare to have an accurate algorithm. And if you look at any journal in numerical linear algebra or scientific computing, there will be a lot of papers coming up on accuracy of various algorithms. Okay, and a lot of those algorithms will be in BLAS only. So accuracy of matrix multiplication even. Okay. uh, accuracy of QR, accuracy of SVD. So various algorithms used for computing these, because accuracy is sort of a difficult thing to achieve. Okay, so people keep on coming up with improvements over the existing algorithms to improve the how do you say, the stability of the algorithm. Okay, so accuracy is difficult to achieve. The next best thing, okay, is stability. Okay, so accuracy, then stability. Stability is of comes in two variants. There is something called as forward stability and backward stability. Uh, so backward stability is something that is more desired in algorithm. And if an algorithm is backward stable, you're all, I mean, that's a very good thing. So it is something that you should aim for in an algorithm. Okay, so let's talk about stability then. So here we have the norm vector space of data, and Y is the norm vector space of solutions. So you have your data points x and x tilde. Okay, under the definition of the problem, x goes to f of x. Okay, and under f tilde, under the algorithm, x goes to f tilde x. Here, f tilde x. Okay. So there are three things to consider here. Okay, so x tilde is a slight perturbation in x. Okay, so let's look at definition of forward stability. So again, on the left hand side we have the measurement of some relative error. But what is this relative error? This is different from what we had earlier. Okay, so we are looking at f tilde x minus f x tilde. So we are looking at the value of the function or the problem at a perturbed point, and this is the computation that you achieve at the original point x. Okay, and so we are looking at this relative error. Okay, and this is being done with respect to the new or perturbed point x tilde. Okay, so what this is saying is that if you compute at the original point x, and if you look at the actual answer at a slightly perturbed point, okay, then the relative error of that or the difference that you get there is bounded above by machine epsilon. So what this is saying is that f tilde will give you the almost the right answer. Okay, so this is to the order of machine epsilon. This means saying you're getting almost the right answer, but to what? Not to fx, but to fx tilde, which is almost the right question. The question also, the data also has been perturbed slightly. Okay, so if you change the question slightly, okay, then f tilde gives you an acceptable answer to that changed question. Okay, so that is forward stability. And backward stability, on the other hand, is what happens if you have f tilde x equal to fx tilde for some slight perturbation. Okay, so here also there was some error, but here we are saying that f tilde gives you the actual right answer to the slightly perturbed question. Okay, so there is equality here, there is no more error. Okay, so f tilde is giving you the correct answer if you perturb your question slightly. That is backward stability. Okay, so we will see how this comes into play when we look at some algorithms. But the thing to remember right now are, if you remember these statements also, okay, the meaning of this. So backward stability will imply forward stability because, well, if your algorithm is backward stable, then these two quantities are equal, which means the numerator here is 0. Okay, so backward stability implies forward stability. And backward error analysis is easier to carry out than forward error analysis. Okay, so this also we will see when we look at the algorithm for Gaussian elimination. Okay, so here are some examples of how these are some very basic examples of how stability analysis is carried out in practice. Okay, so we are looking at some very simple examples here. One is the first one here is subtraction. So the underlying problem is you are given the data x1 comma x2, okay, and you want to calculate x1 minus x2. Okay, so this is the underlying problem, and suppose you write the algorithm for it. Okay, so algorithm here is simply doing the subtraction on the computer, right? So f tilde x1 x2 will be what on computer? This means, well, your x1 is first of all going to be represented by flx1. Your x2 is going to be represented by flx2, and then you are doing the computation on the machine. So that is why this circle represents the computation is happening on the machine. Okay, so by hand it is x1 minus x2, by computer it is flx1 circle minus flx2. Okay, and so we want to compare what is the difference between these two. Okay, we want to see whether or do some stability analysis for this. Okay. So in general, I must warn you that stability analysis is a difficult subject, and stability analysis for if you do stability analysis for some, algorithm, it's like worth a paper. And some stalwarts in numerical linear algebra have already done stability analysis for a number of algorithms that we use today, like Gaussian elimination, QR, um, uh, this LU factorization, Cholesky, all these, okay, that we will see. So those have been done a long time ago, and so they are safely being used now. Okay, but anyway, we can at least try to understand how this process works. Okay. Okay. So what? Let's look at what this means. What FLX1 means. Okay. So by the fundamental property of floating point representations, this FLX1 is going to be x1 times 1 plus some epsilon 1, where mod epsilon 1 is less than machine epsilon. Okay, that's the definition of, or that is what the fundamental property of floating point arithmetic tells for x1. Similarly, this is what it says for x2. Okay, so some epsilon 1 and epsilon 2, which are bounded above by machine epsilon. So we have this first thing. Okay, now we apply the fundamental property of floating point arithmetic. So first we applied it to these two quantities and got our upper bounds. Now we look at the operation itself. For the operation, the fundamental property of floating point arithmetic says that this difference is going to be FLX1 minus, this is the not computed, the actual subtraction, FLX1 minus FLX2 times 1 plus epsilon 3 for some epsilon 3 bounded above by machine epsilon. Okay. So these two statements we are getting from the fundamental properties of floating point representation and floating point arithmetic. Now we put these all together to try and get a relation between this quantity and the original f. Okay. So putting these together, FLX1 minus circle FLX2. Okay, so this is, I'm just going to substitute now in place of FLX1 and FLX2. X1 times 1 plus epsilon 1 minus x2 times 1 plus epsilon 2. And this subtraction is replaced by the whole thing multiplied by 1 plus epsilon 3. Right? So we went from here to this. And now that it is all in the language of x1, x2, and this minus sign, okay, we can try to bring this down to the original problem. Okay, so now just simplifying this. Okay, so I'm multiplying this 1 plus epsilon 3 inside here. Okay, and notice that if I'm both epsilon 1 and epsilon 3 are errors bounded above by machine epsilon. Okay, so this product is going to be bounded above by twice machine epsilon plus machine epsilon square. Okay, so that is this quadratic that appears. Okay, so suppose I have some epsilon 4 and epsilon 5 quantities which are bounded above by this. Okay, then I can replace this whole thing, okay, by x1 times 1 plus epsilon 4 minus x2 times 1 plus epsilon 5. Okay, I just want to get rid of this entire thing and I want to express it in one quantity. Okay, so that's what being done here. Okay, so FLX1 minus circle minus FLX2 is x1 times some 1 plus epsilon 4 minus x2 times some 1 plus epsilon 5. So the computed result, if I, instead of writing this, if I write the computed result, this as x1 tilde minus x2 tilde. Okay. This, where x1 tilde minus x1 over mod x1 is going to be bounded above by some machine epsilon. So actually we can do it this way. So I'm going to write this as this whole thing. Yeah, I've written it here. This whole thing as x1 tilde minus x2 tilde. Okay, so this difference, computed difference, is actually this difference where x1 tilde and x1 are slightly apart. Okay, so these are the difference between these is bounded above by machine epsilon, and x2 tilde and x2 are also slightly apart. So x2 tilde and x2, this relative error is bounded above by machine epsilon, because epsilon 4 and epsilon 5 are bounded above by some quadratic in machine epsilon. Okay, so this is not exactly just constant times machine epsilon. Okay, but you also have this. But the point is that this is going, since machine epsilon is a small quantity, this is going to be even smaller. So you can sort of ignore this quantity and just look at this much. Okay, so you can say that these relative errors are bounded above by machine epsilon. So in the end, what we have got is that the computed result x1 tilde minus x2 tilde, sorry, the machine computation yields x1 tilde minus x2 tilde, where these are slightly perturbed from the original quantities. Okay, and so that because of this equality everywhere, okay, there is no less equal here. Because of this equality everywhere, what this tells us is that subtraction is backward stable. Okay, because this is, if you remember from the definition of backward stability, we wanted this, that f tilde x should be equal to fx tilde. For some x tilde that satisfies this, and that is exactly what we have got here. Okay, this is f tilde x1 comma x2, and on this side we have f. So this thing is f x1 tilde comma x2 tilde. Okay, so f tilde x1 x2 is equal to f x1 tilde x2 tilde, where these two quantities are satisfying this property. So subtraction is backward stable. If I have not written it anywhere, I should write. Therefore, subtraction is backward stable. So, what you need to carry away from this example is that this is how, for every input, you will first use the fundamental property of floating point representation to get these equations, and then use for every arithmetic operation in the algorithm, one uses this fundamental property of floating point arithmetic to get these equations, and then you try to put them together and see if the result comes by a slight perturbation of the data in this way. Okay, so that is the simplest way in which one can describe uh, backward stability analysis. I'm going to leave some of these things to you. So for inner product of two vectors, okay, it can be shown in the with a similar analysis, okay, that x star y, that is inner product, is a backward stable operation. Okay, and so now you can see you have to worry about each of these things. So I just showed you for subtraction. Then this is, you also need to worry whether addition is backward stable, whether multiplication is backward stable, whether uh, division is backward stable, when is it, when it is not. Okay, similarly all these inner product, outer product, matrix multiplications, all these things. Okay, so each one of these was actually proved to have backward stability, uh, yeah, like in the 60s and so on. Okay, 1960s. Okay, so so inner product turns out to be backward stable. Outer product, on the other hand, is stable but not backward stable. Okay, and a sort of heuristic analysis for that can be looked at in the following way. So stable but not backward stable means forward stable. Okay, so if one says only stable with no adjective, then that means forward stable. Okay, because forward stability is very easy to satisfy, and almost everything will satisfy forward stability. So outer product means what? Means you take a column vector and multiply it by a row vector to get a matrix. Okay, this is what outer product means. So outer product is stable but not backward stable, and that can be seen by a simple sort of rank argument. Okay, so I will leave this, or maybe yeah. So what is the rank of a matrix that you get by an outer product this way?
Zero or one.
Yes.
Zero or one.
Zero or
One.
one, right? So that means that when you make an outer product in this way, the rank of this matrix should be one. Okay, and but now look, this is computation, right? This is not by hand. You're doing this on a computer, which means not only were all the entries here rounded off, but all the entries here were also rounded off, and after those multiplication, correct? So for the matrix A to have rank 1, you will need to have all the other columns dependent on one column. Okay, so that is highly improbable in a computed solution. Okay, and so it is highly improbable that this matrix will have rank 1. Okay, and that's a sort of argument to say why this is not going to be a backward stable algorithm. Okay, so the rank of the left hand side is not going to be equal to the rank of the right hand side. Okay. So that's like a very basic property not being satisfied. And of course, one can show this, show that it is not backward stable by arguments like this. So there is one more example that I've stated here that you should look at. Okay, and if you have questions with that, I can take it up in the next class. And there is an example of an unstable algorithm here. Okay, so in the textbook there are these two examples that you should look at once to understand a little bit more about stability analysis. Okay. Yeah, so now one wants to talk about why a backward stable algorithm is preferred. Okay, so what can you say about the accuracy of a backward stable algorithm? Okay, so suppose you have a backward stable algorithm, then how far can you trust it? Okay, so that is given by this theorem. So suppose you have a backward stable algorithm applied to solve a problem F, and suppose that problem F has condition number kappa. Okay, so you have a problem F with condition number kappa and you are applying a backward stable algorithm to it. Then the relative error is going to be to the order of kappa x times machine epsilon. Okay, so if you have a backward stable algorithm, what this theorem is saying is that the stability is, or the accuracy is dictated by the condition of the problem at the given data point. Okay. So you can imagine if this condition is small, then this is a good enough bound. Okay, so no problems with this. But if this condition is really large, then you have a large bound here and it doesn't really say that the relative error is small. Okay, so everything essentially depends on the condition of the problem at the given data point. So for what a backward stable algorithm does is that now the algorithm is good. Okay, so nothing is dependent, or the error is not much dependent on the algorithm, but it is coming down to the condition of the problem itself. Okay, so that is what this theorem says. Okay. I would recommend that you go through this proof. There is nothing difficult. That's the definitions going around. And if you have issues, we can come back to this. Okay, so I think we should go ahead with the next part. So this is something that is part of the sections in Golub and Lohan. Okay, so I would recommend you to read through these sections, at least browse through these sections and the topics in them. Okay, because although we are just going to look at one aspect of the work involved in an algorithm, which is we are going to count each time the number of floating point operations involved. Okay, so when we have algorithm, we will say that the work involved in with this algorithm is these many floating point operations. Okay, so we are going to look at only this aspect, but there is also the cost of moving the data, and there is the cost of storing the data. Okay, so all these things go into the computation when one wants to talk about the efficiency of an algorithm. Okay, so what is the cost of moving? What is the cost of storing? So this is a huge area of research. Okay, cost of reducing the cost of moving the data. Okay, uh, and in technical terms, this is called as communicating. Okay, so if you have, so suppose the data is stored on a number of servers, okay, and for every computation, if you require some piece of data from server one, some piece of data from here, some piece of data from the third one, okay, so that's a lot of back and forth moving of data, okay, and so that adds to the cost. And so algorithms are designed in such a way that that cost is reduced. Okay, so the communication, if you can put all the required elements on one server for one computation. So I shouldn't say anything because I'm not an expert at this. But yeah, so essentially people try to come up with algorithms so that communication is reduced. Okay, so there are communication avoiding versions of various algorithms. Okay, so communication avoiding matrix multiplication, communication avoiding SVD, this and that. Okay, so these algorithms aim to reduce the cost of moving the data. And there is also the cost of storing the data. So of course, when you write an algorithm, you should try and see if some earlier data can now be replaced by new data. If you can just go on updating, okay, no, not updating, just replacing the original data allocation. Okay, so if you have allotted space for some vector and you no longer need it after the first step, then the preferred choice is to replace those spots by the next vector. Okay, so so that is one way in which you can reduce the cost of storing the data. And another uh, way in which the entire cost is reduced is by these things called updation. Okay, so updation. So one example of updation is this Google matrix, right? So the Google matrix. So what the Google matrix does is it is this matrix which comes from all the web links. Okay, and so the compute. I think one of the groups is working on Google matrix, and they will give you a proper description of this at the end. But the point is that this is a huge matrix whose SVD needs to be calculated from time to time. Not SVD, eigenvalue decomposition needs to be computed from time to time. Okay, so if you have this huge matrix and you want to compute its eigenvalue decomposition, you would rather not do it like from moment to moment, right? You would rather not do it uh, every hour or every day. Okay, so actually it is done every day, but you would prefer not to do it every hour because it takes up huge amount of power. Okay, so the thing to do is that whenever the new links come in, the thing to do is try and update this matrix with that new data. Okay, so you have the old data as it is, and just you update some part of this. And if that updation, if there is a way of going from the SVD of the earlier matrix to SVD of this updated matrix, then that is a much sought after algorithm. Okay, so this process is called updation. So you have computed the decomposition for an earlier matrix, and now you have added maybe a row or a column. Does that earlier decomposition give you anything, or is there a way you can get the new computation without having to do the entire decomposition again? Okay, so that is updation, and this kind of updation can save a lot of work. Okay, so this is also one area. So communication avoiding algorithms. This is one area. Communication avoiding. It's called communication avoidance. And another area is updation algorithm. Okay. So I think that updation is something that you will probably see from one of the projects. I think there must be at least one project in which some kind of updation is involved. Okay. So these two tactics are also used to reduce cost. Okay. Anyway, but we will not go for every algorithm that we will study. We will not go into all the. We will only talk about the number of floating point operations when we talk about work. Okay, how many floating point operations are required in that algorithm? Okay, uh, so earlier this used to be a big thing. Okay, like how many floating point operations are required and so on. But now with the increase of computing power, somehow I think in the new era, people don't care too much about this. Okay, unless unless you are talking about the stock market or something where the speed is of real essence, every second is of essence. But otherwise, in general, people won't care too much about this, okay, where you have enough time to work on the algorithm. But still, since we are talking about BLAS algorithms, we will look at the floating number of floating point operations for each of them. Then there is something called as levels in operations. Okay, there are level 1, level 2, level 3 BLAS. Level 1 are those operations which can be expressed as a scalar times a vector plus a vector. Okay, so scalar A times X plus Y. So those things are put together to form this acronym SAXPY. Okay, so SAXPY means operations which can be expressed in this way. Okay, so the operations of this form are called level 1 BLAS. Level 1 basic linear algebra subroutines. Okay, and this you can express this either this way, or you can express it either this way, where this is the updation form of it. Okay, so the new y is obtained from ax plus the earlier y. Okay. So this is level 1 BLAS. Instead of scalar A, if you have a matrix A, okay, then that's called the generalized SAXPY or GAXPY. These are called level 2 BLAS. Okay, and finally, operations which can be expressed as matrix multiplications. Any in an algorithm, if you can express it, express your algorithm as matrix multiplications. Okay, that could also be matrix vector multiplication. But if you can express it in that way, then you have that algorithm written in level 3 BLAS. Okay, and it turns out that so I won't go into too many details, but this is the section that these are the sections that you should read up a little bit for this. Turns out that level 3 BLAS are the most efficient ones. Okay, so oftentimes any algorithm, people will always try to rewrite it or express it in terms of matrix multiplications. Okay, rather than have it expressed in SAXPY or GAXPY, people will want to express it as a matrix multiplication. So we will see this. Oh, not sorry, we will not see this. But I know, I mean, if anybody has studied interpolation before, okay, or I don't know, many different things. Okay, although you have other ways of solving for the problem, the preferred way is to express the whole problem as a matrix multiplication problem. Okay, or solving a system of equation problem. Okay, so these kind of operations are sought after in writing algorithms. Okay. I think I have written down something about uh, the amount, the data and the work required. Okay, so I won't go into the details of this because, well, if you read these sections, you'll get a better understanding of this. Okay, but again, if you have questions, I'll come back to it. Okay, so let me skip this for now, and I want to start talking about Gaussian elimination. So Gaussian elimination, I am sure everybody is aware of how Gaussian elimination is done. So you have a square matrix, and then you try to transform it into an upper triangular matrix, right? So that is by doing row operations. So we'll restrict to row operations. Okay, so if you do row operations to try and obtain an upper triangular matrix. So since you're all aware of this, what I'll do is I'll just state, as I said, although these are row operations, okay, so you can see this is a SAXPY kind of operation, right? So this is subtraction, vector subtraction and multiplication. But we want to express it as a level 3 BLAS. Okay, we want to try and express this SAXPY as matrix multiplication. Okay, so in all the algorithms that you will see, we will have preferably these kind of operations. Okay. Okay, so the first thing when you are given this matrix is to try and make this term 0, okay, or reduce all the terms below the diagonal element in the first row to 0, okay. So to make this 0, everybody knows that we do R2 minus A21 over A11 R1. Okay, so I'm assuming right now for simplicity that all my diagonal elements are non-zero. Okay, and that A is invertible and everything. Okay, so very simple case. So we don't have to worry about whether this element is zero or not. Okay, so this operation I can rewrite as multiplying A on the left by this matrix. Okay, where this matrix is identity except for the element 2, 1. So in the place 2, 1, I have put A21 over A1. So see, what is this going to do? If you left multiply by A by this matrix, this element is going to get multiplied by, to all elements in the first row of A. Okay. And because of where it is one time all elements in the, this is going to be this element times all elements in the first row minus the second row. Okay. So, so this minus is here and this plus is here. So you can sort of imagine what this operation is going to give you. So A11, A12, A1M, A21, A22, A2M. So when you apply the first row, nothing is going to change. Okay, so the first row of this remains as it is. Now, when you apply the second row, then you're always going to get this element multiplied with the first element here plus 1 multiplied with this. This is exactly what this operation is. Okay, so this operation now we are expressing, and that's going to affect only this row. All the other rows are going to remain unchanged. Okay, so the effect of left multiplying with this matrix is going to be the same as this. Okay, is that clear? That is the main point to sort of understand here. Okay, so if it is clear in this case, then the rest of the things are quite simple. Okay, so now you want to repeat this for the third element, A31. So the A31 is R3 minus A31 over A11 R1. This corresponds to left multiplication by the lower triangular matrix. So it's identity except for this element in the 3, 1 spot. Okay, and this is also going to do exactly this operation. Okay, so left multiplication by all these lower triangular matrices. You want to do this to the last element AM1. So we have LM1 being written like this. Okay, so the positioning of this element depends exactly on which row you want to operate upon, and the quantity here, okay, what this element is depends on what element you want to make zero, right? So that is how these, so essentially making all the elements here zero, okay, this subdiagonal first column is same as left multiplying by all these matrices, and so I can express it as this. Okay, so I have I take L21, then to that L31 and multiply that by LM1 on the left. So I take this whole thing to be my lower triangular matrix L1. So if I look at L1A, then the result is going to be this matrix which has all these elements 0, right? So that is L1A. And now what we are going to do is abbreviate these. A21 over A11 we'll call as L21. A31 over A11 we'll call as A31, and so on. And this is something you can check, that if you do this multiplication, okay, these are all lower triangular matrices with a non-zero element only at these spots. Okay, so if you multiply these together, then the corresponding matrix will look like this: lower triangular with these elements coming all in the first column here. Okay. So the net result of ref multiplying A with this L1 is obtaining these zeros here. So you have done all these row operations. Okay. And now this is what we do. We continue with this process. Now we want to obtain the subdiagonal elements below the second, in the second column as 0. Okay, so we want to kill off these elements, and for that we will design this matrix capital L2, okay, by a product of matrices. So here we will have minus L32, where L32 is now A321 by A221. Okay, what is this script 1? The superscript 1 is saying that the elements here are obtained after the first step of elimination. Okay, so because when you do this operation, this submatrix is going to change. Correct. This multiplication by this lower triangular matrix won't affect the first row of A, but it will affect all the elements from the second row onwards. Okay, so all these elements are going to change. So this superscript 1 is saying whatever this element is at the end of the first step. Okay, and so this is going to be the element which you require to be non-zero. So let's just suppose it is non-zero and move on. Okay, so suppose this element is non-zero, then you can design your next matrix L32 in this way. Okay, and up to the last one, and then your capital L2. Okay, so although I have not written it here, your capital L2 will also be a lower triangular matrix with these kind of elements in the second column. So you will have 0 and minus L32 minus L42 dot 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 minus LM2. This is how your capital L2 will look like. So you have your L1A already computed, and to that, if you apply L2, then you will obtain a matrix in which the elements below the diagonal in the second column are 0. Okay, and this is how we proceed. Then for the third column, you form a matrix L3 that will kill off elements below diagonal in the third column, and so on. And you have to keep on doing this till not the last column, but the one but the last, right, up to this one. So you do this up to m minus 1. So we design these lower triangular matrices, and the application of each one on the left is going to kill off subsequent columns below the diagonal. Okay. Is this process clear? Once this basic process is clear, the rest of it is not so difficult. Any questions here?
No, ma'am. Clear.
Okay, thanks. So in the kth step, okay, so I have written kth step here because when we write the algorithm for this, it will be useful. Okay, this notation will be useful for us in the algorithm. So I've written AK minus 1. So how is AK minus 1 obtained? So what we'll do is we'll denote L1A by A1. Okay, so A1 is what you obtain by multiplying by L1. So A2, and then A2 is what you will obtain by pre-multiplying L1A by L2, and so on. Okay. So in A2, the second column has been filled off. Okay, subdiagonal elements in the second column. So which means in AK minus 1, we have subdiagonal elements in the K minus 1th column killed off. Okay, so we are already here. And the elements here, you see, we have superscript 1 for the second row, because these elements are not changed after the second operation. Okay, for the third operation, these remain the same. Okay. Similarly, the elements of the third row will remain the same after the third matrix is applied. Okay, after that, nothing is going to change this. So whatever these elements were at the end of the second step, they will remain like that till the end, and so on. Okay, so you see here now these are K minus 1. So we have done the K minus 1 application. We have gotten these zeros, and whatever these elements are now, so in this submatrix here, okay, these elements are whatever is obtained at the end of the K minus 1 application. Okay, so that is where we are at AK minus 1. Now for the next column K, LK is designed like this as usual. Okay. So Lk plus 1k, this element, okay, is Ak plus 1k obtained in the k minus 1th step divided by Akk obtained in the k minus 1th step. Correct? So that is what we have here. Okay, up to Lmk. Okay, although I think I'm missing a minus sign here. That's right. I'm missing a minus sign here. There should be a minus. Yeah. So that is what Lk is. Okay. And Ak is going to be Lk applied to Ak minus 1. So you continue in this way. See, this is the step which is going to be useful for us in terms of the notation when we write the algorithm. So continuing in this way, you just apply all these matrices to A and you will end up with an upper triangular matrix. Call that upper triangular matrix U. Okay. And now if we rearrange these terms, okay, so first of all, thing to remember is that if you have a lower triangular matrix, then its inverse is also going to be a lower triangular matrix. Okay, if you have not seen this before, then it's time for you to check it. And if you have upper triangular matrix, the inverse is upper triangular. If you have a lower triangular matrix, the inverse is lower triangular. So what I'm going to do is now I'm going to just rearrange this by sending all this to the other side. Okay, so when we send this to the other side, of course, we have to take inverses. Okay, so let L be this matrix, the product of the inverses L1, L1 inverse, L2 inverse up to Lm minus 1 inverse. Then you will have written A as L times U. Okay, where L is a lower triangular matrix because it is a product of lower triangular matrices, and U is the upper triangular matrix that you obtain by this reduction. So essentially, this process of elimination or Gaussian elimination, as it is called, gives you a factorization of the matrix A. Okay, in the form of a lower triangular matrix times an upper triangular matrix. This is called the LU factorization. Okay, so notice that this L. Okay, so this is also something you should check. What is L1 inverse? What is L2 inverse? What is Lm minus 1 inverse? So remember what L1 was. L1 had these elements, right? So you can check that if you take these elements with a plus sign, that's exactly what is going to be the inverse of L1. Okay. So it will turn out in the end that L has this form. Okay. So this is something you probably should check. Check that L actually has this form. Okay. And it is clear that since you have ones on the diagonal, the determinant of the cell is 1. Okay. So this particular factorization of A is called the LU factorization. Are there any questions till this point? Okay. So remember that in this simple description, we had assumed that A11 is 0, and then we assumed at every step that the element by which you need to divide, so A221 here, okay, and in general, this AKK K minus 1 for every step K. We have assumed that this is non-zero, okay, and with that assumption, everything went smoothly, okay. But in practice, you need not have this, okay, and you need not get this AKK minus 1 0 each time, okay. So one has to deal with that fact, and for that one has to introduce something called as pivoting. Okay, so pivoting, there are many ways of doing pivoting, and people have come up with better and better ways to sometimes to improve the stability of the algorithm. Okay, so not sometimes actually. The reason why various pivoting algorithms exist is exactly to improve the stability of the algorithm. Okay, make it more and more stable. So one of the easiest way of so we will study or look at in the beginning one of the easiest way of doing this. Okay, so the easiest way is suppose you are working with the kth column now. Okay, and so you are worried about whether this element is 0 or not. Okay, so instead of checking whether this is zero or non-zero and all that, okay, simply look at the maximum in absolute value. Look at the maximum among the elements in this uh, piece of the column. Okay, and replace the maximum. So suppose that maximum element appears somewhere here, just replace these two or exchange these two elements. Okay, so you replace this pivot, this element is called the pivot. You replace the pivot by the maximum in absolute value of all the elements in that subcolumn. Okay, so this is the easiest way of doing pivoting. Okay. Now there are variations to this. Instead of looking at the maximum among these, okay, one could also look at the maximum among, well, of course, you could have looked at maximum among these, but that's no use because you are really doing the operation here. Okay, so the other way is to look at maximum among all these. Okay, so you look for the maximum element among absolute values of all this, all the elements in this submatrix, and replace the pivot element by that. Okay, another, so that is called as, so if you're looking only at this, okay, then that is called as partial pivoting. If you look at all elements here, that is called as complete pivoting. Okay, there is one more way. This will be part of your homework. Is you look at these elements. Okay, this is called as rook pivoting. Okay, and rook pivoting has been shown to improve stability considerably. Okay, so among these three methods that I told you, okay, so partial pivoting offers some stability. Okay, it makes the algorithm acceptable, but it's not the best. It can be improved. Okay. On the other hand, as you would expect, complete pivoting offers the best stability. Okay, very stable algorithm. But see, in complete pivoting, there are all these comparisons to be done. Okay, so that increases the amount of work that needs to be done to choose the pivot. Okay, it turns out that the rook pivoting strategy meets both these halfway. Okay, so this strategy turns out to be as stable as complete pivoting, okay, and doesn't require too many operations more than the partial pivoting strategy. Okay, so rook pivoting is a also commonly used strategy in Gaussian elimination. Okay, so this was about pivoting strategies. So let's just continue with the simplest pivoting, which is partial pivoting. Okay, so again, pivoting or this exchange of elements, it, see, exchanging elements is not a floating point operation. It's not addition, subtraction, multiplication, division, etc. Okay, so exchanging elements is not a floating point operation. However, you would like to frame it as a matrix multiplication. Okay, and for that one can note that if you multiply by, so these kind of matrices where you have the identity matrix and one row is exchanged with another row. Okay, or two, so rows are exchanged or two columns of exchange are exchanged. Such a matrix is called an elementary matrix. Okay, so this is an example of an elementary matrix. You took the identity matrix and exchanged the first and the jth column. Okay, then whatever you get, that's an elementary matrix. Okay, turns out that these exchanging of elements or exchanging of rows or exchanging of columns, any of these can be expressed as multiplication, either pre or post multiplication, depending on what you want. Multiplication by elementary matrices of these kinds. Okay, so if suppose you want to do this exchange that I was saying here. Okay, so suppose you want to exchange this element with some element here. Okay, then the exchange is not going to be just the elements. You will have to exchange the entire row with this entire row. Okay, so it's going to be a row exchange. So you cannot just exchange these two elements. So this entire row exchange can be implemented by pre-multiplication by a matrix by an elementary matrix of this kind. Okay, so to see that, first let's see what if you want to exchange rows j and 1, let's say. Okay, so exchanging rows j and 1 is same as what pre-multiplying by the elementary matrix E1j, where the first and the jth rows or columns are exchanged. Okay, so this you can, if you are not convinced, you should quickly do a 3 by 3 example and check. Okay, so take a 3 by 3 elementary matrix. Okay, elementary means what? You have the identity matrix and now you're exchanging. Okay, so suppose I exchange the first and the third rows. Okay, so now we'll have 0, 0, 1, 1, 0, 0. So this is going to be the matrix E13. So pre-multiplying this with some matrix is going to, so if I do this pre-multiplication, the result is going to be exchanging of the first and the third rows, because I did exchange in the first and the third rows here. Okay, and it's easy to convince yourself, because what multiplying by this does is exactly picks up the elements in the third row and puts them in the first one. Okay, so this is going to be the result of pre-multiplication. And you should also check what is the effect of post-multiplication. Which means now if I took this matrix and multiplied it to this matrix on the right hand side, then what will happen? Okay. So what happens if you post multiply is that instead of rows, columns get exchanged. Okay. So if you want to exchange rows, you do pre-multiplication. If you want to exchange columns, you do post multiplication by elimination.